A frozen world spins frantically in the deep dark. What is Varuna hiding out there on the solar system's fringe? This distant object, a major denizen of the Kuiper belt, is a vault of cosmic secrets. We are about to unravel 25 of its most baffling and unexplained mysteries. You will discover why this icy dwarf planet defies our basic understanding of worlds. How can it spin so fast without tearing itself apart? Why does it appear to be a strangely stretched-out shape? What single mystery of Varuna captures your imagination the most? Its frantic spin is the first great puzzle. A day on Varuna, the time it takes to complete one full rotation, is a mere 6 hours and 20 minutes. For an object estimated to be over 400 miles across, this speed is staggering. To put that into perspective, if Earth spun that fast, our planet would literally fling itself to pieces. So what keeps Varuna intact against such tremendous centrifugal forces? The leading theory suggests it is not a solid, rigid sphere of rock and ice. Instead, scientists propose Varuna is what is known as a rubble pile, a collection of countless boulders, rocks, and ice chunks all loosely held together by their own collective gravity. Think of it not as a single stone, but as a gigantic, spinning bag of cosmic gravel. This structure allows it to flex and absorb the stresses of its rapid rotation, behaving more like a fluid than a solid world. This single characteristic hints at a violent past, perhaps formed from the gentle collision and accumulation of smaller bodies that never fully fused into one. The very speed of its spin becomes a clue, a lasting echo of the chaotic processes that built our outer solar system. That incredible spin leads directly to another void, the puzzling lack of a known atmosphere. While its distant cousins Pluto and Eris are known to possess thin, tenuous layers of gas, Varuna appears to be utterly bare. This is deeply strange for a world composed largely of volatile ices, materials that should readily turn to gas when warmed by the distant sun. So where did its atmosphere go? One compelling theory points back to its frantic rotation and relatively weak gravity. The combination may have simply been too feeble to hold onto any gases that tried to form. Imagine a world trying to grasp smoke with open fingers, the particles easily drifting away into the vacuum of space. Another possibility involves temperature. Even in the profound cold of the Kuiper belt, Varuna might be just a little too warm. If its surface ices are not cold enough to remain completely frozen, they would sublimate, turning directly from solid to gas, but without sufficient gravity to keep that gas anchored, it would be lost almost instantly. This absence defines the very nature of its surface. Without an atmospheric blanket to distribute heat or shield it from impacts, Varuna's landscape would be one of extreme contrasts, with surface temperatures plummeting to near absolute zero in the shadows while any area facing the sun bakes, relatively speaking. It is a silent, airless realm where no wind blows and no sky exists, just the stark, black curtain of space directly above. This bizarre lack of an atmosphere sets the stage for an even stranger physical truth. Varuna itself is not the round world we might expect. The evidence points to a body that is dramatically elongated, more akin to a cosmic potato or a stretched-out egg than a neat sphere. This conclusion comes not from a direct photograph, but from a careful study of its light. As Varuna spins, the amount of sunlight it reflects back to us changes in a distinct, rhythmic pattern known as a light curve. A spherical object would show almost no variation, but Varuna's light curve is extreme, telling astronomers that different, vastly unequal sides are rotating into view. One of its dimensions could be nearly twice as long as another. For an object of its substantial size, this is profoundly unusual. Gravity typically forces larger bodies into a spherical shape, a state called hydrostatic equilibrium, where self-gravity pulls all material toward a central point. So why is Varuna not round? One compelling theory is that it is a contact binary. Imagine two smaller, separate bodies, each a world in its own right, slowly drifting together over eons until they gently touched and stuck, forever frozen in a clumsy embrace. Their combined mass was never quite enough to remold them into a single, round sphere, leaving behind a merged, lumpy shape. Another, more violent possibility is a recent catastrophic collision. A tremendous impact with another Kuiper belt object could have shattered Varuna's original form, leaving behind a distorted remnant that is still slowly settling, or perhaps will forever remain locked in this stretched configuration. This peculiar shape forces us to reconsider what it means to be a planet, even a dwarf one, and hints at a formation history far more chaotic and less orderly than we once believed. This distorted shape makes pinning down its true size a surprisingly difficult task. For years, astronomers have been locked in a debate over a fundamental question: is Varuna a large, dark world or a much smaller, brilliantly reflective one? The answer depends on a property known as albedo, which is simply a measure of how much light a surface reflects. A pristine, white ice sheet has a very high albedo, while a surface of dark, sooty carbon has a very low one. We cannot directly measure Varuna's diameter from Earth, so scientists must combine its perceived brightness with an assumed albedo to estimate its size. This is where the mystery deepens. If we assume Varuna has a dark, charcoal-like surface, similar to many comets, then it must be quite large, perhaps over 420 miles across, to account for the faint light we see from it. But if its surface is instead covered in bright, fresh ice, then it could be a much more compact object, perhaps only 340 miles in diameter. That is a staggering difference, nearly 80 miles of uncertainty. This is not just a matter of numbers, it strikes at the very heart of what Varuna is made of. A bright surface suggests recent geological activity or impacts that exposed clean water ice, while a dark surface points to an ancient, primordial crust covered in dark organic compounds baked by eons of cosmic radiation. Our entire understanding of its density, its mass, and its internal structure hinges on resolving this single, perplexing enigma. How can a world so significant to our solar system's history remain such a profound question mark in our most basic measurements? The secrets of its size are locked within the chemistry of its surface. When astronomers point their most powerful telescopes toward Varuna, they are not capturing detailed images, but rather reading its light signature, a spectrum that reveals the fingerprints of its composition. This data paints a strange and complex picture. Varuna's surface is not a single, uniform substance, but a patchwork of water ice and something far more enigmatic, complex organic molecules called tholins. These are not signs of life, but the building blocks for it, formed when simple ices like methane and nitrogen are bombarded by cosmic radiation over billions of years. The process is a slow, patient chemistry experiment conducted in the deep freeze of space. Imagine sunlight and cosmic rays over eons, slowly cooking the frozen surface, breaking apart simple molecules and reassembling them into complex, tar-like compounds that are dark and reddish in color. This is what gives Varuna its potentially muted albedo and its cryptic, rusty hue. Yet this discovery only deepens the mystery. Why does Varuna appear to have a different mix of these materials than many of its Kuiper belt neighbors? Some objects out there are brilliantly white, while others are jet black. Varuna seems to occupy a strange middle ground. Its specific spectral signature suggests a surface that has been altered, but not completely transformed. Perhaps its rapid spin and elongated shape create unique temperature gradients, where some areas are cold enough to preserve pristine ice while others are warm enough to accelerate this cosmic chemistry. Or maybe its history involves a recent impact that stirred its surface, bringing fresh, clean ice from the interior up to mix with the ancient, irradiated crust. The presence of tholins is a fossil record written in chemistry, hinting at processes that have been continuously at work since the birth of our solar system. What does it mean that such complex organics can form and persist in the most frigid, sun-starved reaches of our cosmic neighborhood? This dark, red coating is more than just color. It is the ghost of billions of years of silent, radioactive alchemy. Those complex organic tholins are not spread evenly across Varuna's surface. This becomes stunningly clear when we observe its light, not just its color. The variations in its brightness as it spins are far more intricate than a simple elongated shape can explain. A perfectly smooth, stretched-out world would still produce a predictable two-peaked light curve. Yet the fluctuations we see are more complex, suggesting a surface of dramatic contrasts. It is as if we are watching a tumbling, irregular stone with one half painted matte black and the other coated in brilliant white frost. This tells us that Varuna possesses genuine topography, a landscape of shadows and highlights we can only infer. What could these dark and bright patches be? One compelling possibility is vast impact craters. A deep, shadowed basin would appear significantly darker than the surrounding terrain, especially on a world with no atmosphere to scatter light and soften the shadows. Alternatively, these could be different geological provinces. Perhaps ancient, dark plains of irradiated tholins lie adjacent to younger, brighter regions where a recent collision or some form of internal activity has scraped the surface clean, exposing the pristine water ice beneath. This is our most direct, albeit blurry, window onto the actual terrain of this distant world. The subtle dance of its light is a coded message describing mountains we cannot see and valleys we can only guess at, a full cartography of mystery written in flickers of reflected sunlight. This intricate surface, a map of light and shadow, circles a world utterly alone. The deep and extensive searches for any moons orbiting Varuna have yielded a profound and surprising result: nothing at all. For such a substantial object in the Kuiper belt, this solitude is deeply unusual. Most large bodies out there, like Pluto with its 5 moons or Eris with its satellite Dysnomia, are accompanied by smaller partners. These orbiting companions are thought to be common relics from the violent collisions and gentle accumulations that built the outer solar system. So why is Varuna the exception? Why does it travel through the void in complete isolation? One compelling theory suggests its formation history was uniquely peaceful. Perhaps it coalesced from a cloud of material without experiencing a major moon-forming impact. Think of it building up slowly, like a snowball rolling down a gentle hill, gathering dust and ice without a single disruptive crash that could have flung debris into a stable orbit. Another, more dynamic possibility is that Varuna did have moons once, but they were stripped away by gravitational interactions. In the crowded and chaotic early days of the Kuiper belt, a close pass with another large object could have easily plucked a small moon from its gravitational embrace, sending it drifting off into the darkness forever. This profound loneliness forces us to reconsider the typical life story of a dwarf planet. It presents Varuna not as a system, but as a solitary wanderer, a testament to a quieter, or perhaps more eventfully tragic, past that left it sailing on its own. This profound solitude extends to its very path around the sun. Varuna's orbit is not a serene, predictable circle, but a stretched and tilted ellipse, a cosmic roller coaster ride that speaks of a deeply troubled past. Its journey takes it from a relatively close but still incredibly distant point near the orbit of Uranus all the way out to the frozen fringes of our system. This path is also tilted, running at an angle to the orderly plane where most planets travel. Such a chaotic orbit is a clear signature of a violent history, a gravitational scar telling a story of cosmic upheaval. So how did a world of this size end up on such a wild trajectory? The leading theory points to a colossal event in our solar system's youth, a period known as the planetary migration. Billions of years ago, just after the planets formed, they were not locked in their current stable orbits. The giant planets Jupiter, Saturn, Uranus, and Neptune are believed to have shifted their positions in a grand gravitational dance. As they migrated, their immense gravity would have acted like a wrecking ball on the primordial disk of smaller objects surrounding them. Worlds like Varuna, which may have formed much closer to the Sun in a more orderly region, were violently flung outward, scattered like billiard balls into the darkness. Varuna's present eccentric path is a perfect fossil of that event, a frozen record of that ancient chaos. Its specific orbital parameters are clues, allowing astronomers to run computer simulations backward in time to trace its probable origin. This suggests it is not a pristine, primordial object that formed peacefully in the Kuiper belt, but rather a refugee, an immigrant from the inner solar system that was brutally exiled to the frozen outskirts. Every loop it makes around the Sun is a silent testament to a time when the architecture of our cosmic neighborhood was being violently remade. This wild orbital journey, a path carved by ancient chaos, raises a startling question about the world itself. Could this frozen, distant sphere harbor geological fire within its icy heart? The possibility exists that Varuna may possess, or may have once possessed, cryovolcanos. These are not the fiery mountains of Earth, but their frigid counterparts erupting a slow, thick slurry of water, ammonia, or methane slush. On a world so far from the Sun's warmth, the very idea seems contradictory. What possible heat source could melt ice from within to power such eruptions? The answer may lie in its very formation. When Varuna coalesced from the primordial cloud of dust and ice, the energy from countless impacts and the compression of its own material would have generated immense heat, trapping a warm core within its frozen shell. But that was billions of years ago. For activity to persist today, or even in the geologically recent past, another mechanism is needed. The most likely candidate is the slow, persistent decay of radioactive elements locked deep within its rock. Elements like potassium-40 and thorium-232 release heat as they break down over eons, providing a steady, if faint, internal furnace. Another, more exotic possibility involves its rapid spin and peculiar shape. The constant flexing and stretching from its rotation could generate tidal friction inside the world, much like repeatedly bending a piece of metal until it grows warm. This internal heat from whatever source would seek a way to escape. If the pressure built sufficiently, it could force a slushy mix of water, ammonia, and other antifreeze materials upward, fracturing the brittle outer crust and oozing out onto the surface in a slow, freezing eruption. Imagine not a river of lava, but a glacier being born from within, a viscous flow that slowly solidifies into new, exotic landscapes. The search for evidence is the next great challenge. Future missions would scan its strange, elongated shape for specific surface features, like gentle, rounded domes that could be frozen cryovolcanic vents, or vast, smooth plains that might be the frozen flows of ancient eruptions. Finding such a feature would fundamentally reshape our understanding of this distant world. It would transform Varuna from a simple, inert frozen ball into a geologically active, or at least recently active, world with a complex internal life, a place where the hidden fires of creation still whisper beneath the ice. That potential for hidden fire connects to an even grander idea. Varuna may be more than just a world, it could be a perfect cosmic time capsule. Locked within its frozen heart could be pristine materials from the very cloud of gas and dust that gave birth to our entire solar system. This is the profound mystery of its primordial composition. While the inner planets were baked and battered into new forms by the heat of the young sun, the distant Kuiper belt remained a deep freeze. Out there, the original building blocks of planets may have remained untouched for 4.6 billion years. Studying Varuna is not just observing a distant object, it is like opening a geological freezer and tasting ingredients from a recipe that was made before Earth even existed. So what exactly is preserved within its ice? The fundamental unanswered question is about the exact composition and conditions of that protoplanetary disk. Was it a uniform mixture, or were there distinct zones of different materials? Did the outer disk where Varuna formed contain a specific cocktail of ices and rocks that is different from what we see in the inner solar system? By analyzing the ratios of different isotopes in its water ice, or identifying rare hypervolatile gases trapped in its structure, scientists could reconstruct the temperature and density of the primordial cloud. Think of it as finding an ancient, unopened jar in a tomb. The contents are not just a curiosity, they are a direct chemical message from a lost era. Every chunk of ice on Varuna's surface could be a page from the solar system's first chapter, written in a language of molecules that we are only just learning to read. What secrets about our own origins are we missing, simply because we have not yet been able to reach out and sample this frozen relic from the dawn of time? This puzzle of its primordial composition leads us to a more fundamental question: what is Varuna actually made of? The answer lies in its density, a simple measure of how much mass is packed into its volume. Yet for this distant world, calculating that number has proven to be a monumental challenge. Without a moon to help us measure its gravitational pull, its mass remains a guess. And without a clear picture of its exact size and shape, its volume is equally uncertain. This creates the density dilemma. The estimates we have, based on the best available data, point to something astonishing. Varuna's density appears to be remarkably low, potentially even lower than that of pure water ice. If you could place a chunk of Varuna in a cosmic ocean, it would not sink but float. This makes no sense if it were a solid ball of rock and ice. Rock is heavy, so how can a world be less dense than ice alone? The explanation points to a startling internal structure. One possibility is that Varuna is incredibly porous, like a cosmic sponge or a freshly fallen snowbank. Its interior may be a labyrinth of vast empty spaces and caverns, left over from its formation or created by the gentle settling of its rubble pile structure over billions of years. Another, equally compelling idea is that its composition is dominated by lighter ices like frozen methane or nitrogen. These substances are far less dense than water ice, and if they make up a significant portion of Varuna's bulk, they could pull its overall density down dramatically. This mystery gets to the very heart of what this world is. Is it a solid, cohesive sphere, or is it a fragile, loosely packed aggregate, a celestial ghost held together by the faintest whisper of its own gravity? The answer would tell us not just what Varuna is, but how it came to be, revealing whether it formed quietly from a gentle accumulation of frosty dust or was assembled in a violent collision that left it forever hollowed out. This deep red hue is not a simple coat of paint, but a cosmic chronicle written in radiation. Varuna presents us with a distinct color conundrum, a surface that glows with a rusty, reddish tint common among its Kuiper belt neighbors, yet unique in its specific shade. Why is this world, and so many like it, colored this way? The answer lies in a slow, patient alchemy driven by the most powerful forces in the universe. The primary ingredients are simple ices, frozen methane and nitrogen, that have blanketed Varuna's surface for eons. But the catalyst is relentless bombardment, a rain of solar ultraviolet light and high-energy cosmic rays from deep space. Over billions of years, this radiation acts like a microscopic chef, breaking apart the simple molecules of methane and nitrogen and reassembling them into complex, tar-like organic compounds known as tholins. These tholins are the source of the red. They are not evidence of life, but they are its chemical precursors, the kind of complex carbon-rich materials that could eventually lead to biology under the right conditions. So the mystery is not really why Varuna is red, but why it is not redder, or why its redness differs from other objects in the same frozen realm. This variation is the true puzzle. Some Kuiper belt objects are a brilliant neutral white, while others are so dark and red they are nearly black. Varuna sits somewhere in the middle. This tells us that the tholin creation process is not uniform. It depends on three key factors: the original composition of the surface ice, the length of time it has been exposed to radiation, and whether that surface has been disturbed. A world with a lot of fresh, clean water ice exposed by a recent impact will appear brighter and less red. A world whose surface has been left untouched for billions of years will have developed a thick, dark red crust of tholins, a patina of extreme age. Varuna's specific hue suggests a surface that is neither brand new nor ancient beyond measure. Perhaps its frantic spin and elongated shape create microclimates where some areas are more heavily irradiated than others. Or maybe its history includes occasional resurfacing events where geological activity or smaller impacts stir the pot, churning up brighter material from below and mixing it with the older, redder top layer. Its color is a clock, a thermometer, and a history book, all fused into one cryptic reddish glow. That deep red patina, a chronicle of eons of radiation, might not be a permanent feature. Could a world like Varuna, spinning so far from the sun and with minimal axial tilt, actually experience seasons? The very idea seems impossible. Seasons on Earth are driven by our planet's pronounced tilt as we orbit the sun. But Varuna's tilt is negligible and its sun is a mere pinprick of light. Yet over its immense 283-year journey around our star, it does not travel a perfect circle. Its elliptical path brings it from a closer point near Uranus's orbit to a much more distant one. This change in solar distance, though it involves temperatures only a few degrees apart in the realm of absolute zero, could be enough to trigger a slow cosmic breath. When Varuna is at its closest approach to the sun, that minuscule increase in solar energy might be just sufficient to cause the most volatile ices on its surface, like frozen nitrogen or methane, to sublimate. They would turn directly from solid to a tenuous gas, but without a real atmosphere to speak of, this gas cannot travel far. Instead, it might drift across the surface, carried by the faintest of thermal currents, until it reaches a cold trap, a permanently shadowed crater, or a region turned away from the sun. There, in the profound chill, the gas would recondense, falling back as a fresh layer of glittering frost. This process would slowly, over decades, paint and repaint the landscape. A dark, tholin-stained plain could gradually be covered by a bright, reflective sheet of new ice, dramatically altering that region's albedo. From our vantage point, this could manifest as a subtle, long-term change in Varuna's overall brightness or the pattern of its light curve as it spins. We are essentially looking for a world that is slowly changing its spots over the course of a human lifetime. Detecting such a cycle would be a monumental achievement, revealing Varuna not as a static, frozen monument, but as a world with a slow, rhythmic pulse, a place where the faintest whisper of sunlight can still choreograph a dance of ice across the ages. This profound solitude extends beyond its lack of moons to a cosmic family it should have, but does not. In the bustling asteroid belt, when a large object shatters, its fragments stay together as a clan, all sharing a similar orbit that points back to a single, violent origin. For a world like Varuna, whose stretched shape and frantic spin strongly suggest a catastrophic impact, this presents a deep puzzle. Where is the Varuna family? If a colossal collision indeed sculpted its bizarre form, the cosmic debris from that event should still be nearby, a cloud of siblings tracing the same path around the sun. Yet our searches have found nothing. No cluster of objects with matching orbits has been identified. This absence is a glaring contradiction. It forces us to reconsider what kind of impact shaped this world. Perhaps it was not a disruptive smash, but a gentler, merger-style collision, where two bodies came together so slowly that they created little debris, like two snowballs softly combining into one lumpy mass. Another, more dynamic possibility is that the family did once exist, but the gravitational turmoil of the early solar system, the same chaos that gave Varuna its wild orbit, also scattered its kin to the cosmic winds. Over billions of years, the subtle gravitational nudges from Neptune and the other giant planets could have slowly pulled the fragments away, dispersing them across the Kuiper belt until their family resemblance was completely erased. This missing clan is more than just a collection of absent rocks. It is a challenge to our entire understanding of how collisions work in the frozen depths of space, suggesting that the history of this region is even more complex and erasive than we ever guessed. This potential for a slow, rhythmic pulse of surface change hints at something even more profound stirring deep within. Could the chaotic forces that shaped Varuna's past be actively warming its interior to this very day? The possibility exists that this distant, frozen world might conceal a liquid water ocean, a hidden sea locked beneath miles of solid ice. The concept seems to defy all logic. How could liquid water persist so far from the sun's warmth, where surface temperatures are colder than any earthly winter? The answer lies in a combination of internal heat and powerful antifreeze. The most reliable furnace is the slow, persistent decay of radioactive elements like potassium and thorium, locked within the rocky material mixed with its ice. This radiogenic heat provides a steady, faint warmth, a background glow that has lasted for billions of years. But Varuna has another, more unique potential source: its frantic 6-hour spin. The constant centrifugal force from this rapid rotation, combined with the gravitational tugging from the sun over its eccentric orbit, could create internal friction, flexing and kneading the world's interior. This process, known as tidal heating, generates additional warmth, the same kind of energy that fuels the dramatic volcanoes on Jupiter's moon Io, albeit on a much smaller, quieter scale. This heat, however slight, would be enough to soften the ice, but to create a true liquid ocean, it needs a partner. That is where ammonia comes in. Common in the outer solar system, ammonia acts as a potent antifreeze when mixed with water, dramatically lowering its freezing point. A slushy layer of water and ammonia could remain liquid at temperatures far below what pure water could endure. The implications of such a discovery would be staggering. Where there is liquid water, chemical energy, and organic compounds like the tholins on its surface, the basic ingredients for life as we know it are present. While Varuna itself is a long shot for harboring biology, the mere existence of a subsurface ocean would prove that liquid water can exist in the most unexpected places, vastly expanding the habitable zone of our solar system and the galaxy. It would transform our view of these distant icy worlds from inert fossils into dynamic, potentially life-friendly environments, each a sealed capsule of primordial chemistry with its own hidden story. This cosmic loneliness stands in stark contrast to one of its most peculiar neighbors. The dwarf planet Haumea presents a mirror image of Varuna in some ways, yet its story is dramatically different. Haumea also spins with a frantic velocity, completing a day in less than 4 hours. It is also wildly elongated, shaped like a flattened football, and crucially, Haumea is not alone. It is surrounded by a family, 2 known moons, and a swarm of smaller objects, all sharing a similar orbital heritage, the clear debris from a gargantuan impact in the distant past. So why does Haumea have this cosmic clan while Varuna travels in utter solitude? The similarities seem too profound to be mere coincidence. Both are large denizens of the same frozen realm. Both bear the scars of what should be a collisional origin. This presents a fascinating mystery. Do Varuna and Haumea represent a common class of object, a standard outcome from the violent construction of the Kuiper belt? Or did they form in entirely different ways, their similar shapes and spins emerging from distinct processes? One compelling theory suggests the difference lies in the violence of the impact itself. Haumea may have suffered a truly catastrophic high-energy strike, a blow that shattered its original form and sent a cloud of debris spinning into orbit. Varuna's impact, by contrast, could have been a much gentler, grazing collision, a slow-motion merger that stretched it into its current shape without generating enough escape velocity to launch permanent satellites. Another possibility involves location and timing. Perhaps Haumea's family-forming collision happened later, after the great planetary migration had settled down, allowing the debris to remain clustered together. Varuna's ancient impact, however, might have occurred right in the middle of that gravitational chaos, its potential family instantly scattered by the shifting giants, leaving no trace for us to find today. The haunting question remains, is Varuna the rule, or is it the exception? Are most of the solar system's original impact families long since erased, with Haumea's clan being a rare, preserved relic? Or is Haumea the standard, and Varuna's solitary nature the true anomaly, a quirk of a uniquely peaceful or tragically disrupted history? The silent dialogue between these two misshapen worlds forces us to reconsider the entire narrative of the outer solar system's formation. That hidden potential for a liquid ocean rests entirely on a single, measurable property: heat. How this distant world manages its energy is one of its most fundamental and puzzling secrets. We know Varuna's surface is brutally cold, likely hovering around -220 degrees Celsius, a temperature where air itself would freeze solid. This is exactly what we would predict for an object so far from the Sun. Yet when astronomers study Varuna in the infrared part of the spectrum, measuring the heat it radiates back into space, the observations do not quite match the simple, frozen billiard ball model. The thermal emissions are slightly off, suggesting its surface temperature is not perfectly uniform or that it retains heat in strange ways. This thermal discrepancy is a critical clue, a faint signal that something unusual is happening on and just below its surface. The mystery lies in what is causing this subtle anomaly. One compelling explanation points to surface texture. Imagine two surfaces left out in a freezing night, one a smooth sheet of ice, the other a fresh, fluffy snowbank. Both are the same material, but the snowbank, with its countless tiny air pockets and complex structure, is a fantastic insulator. It traps heat, preventing it from escaping easily. Varuna's surface might be more like that snowbank than a sheet of ice. It could be incredibly porous and rough, covered in a fine, frosty dust or a labyrinth of tiny cracks and shadows. This microscopic terrain would create a complex thermal landscape. A smooth surface would cool off rapidly and evenly, but a rough one would have sunlit peaks radiating heat while deep, shadowy pores remained comparatively warmer, confusing our remote measurements. Another possibility involves its internal composition. If Varuna's crust is a poor conductor of heat, perhaps due to layers of insulating tholins or low-density ice, it could trap the faint warmth from its interior, preventing it from dissipating directly into space. This would create a slight thermal lag where the surface is not in perfect equilibrium with the bitter cold of space. Solving this thermal puzzle is not just an academic exercise, it is the master key to interpreting every other observation we make. The way Varuna manages its heat directly influences how we calculate its size, estimate its composition, and even speculate about its internal structure. A world that holds onto its heat a little too well might be hiding a warmer, more dynamic interior than its frozen exterior would ever suggest. That bizarre, stretched-out shape of Varuna forces a radical rethinking of its very origin. One of the most compelling explanations for its form is that we are not looking at one world but two. This is the contact binary hypothesis, a theory suggesting Varuna was born from a gentle cosmic kiss. Imagine two separate, smaller bodies, each a nascent world in its own right, orbiting one another in the solar system's early darkness. Over time, their mutual gravitational dance slowly decayed, drawing them closer and closer in a spiral that spanned eons. Their final meeting was not a cataclysmic crash, but an incredibly slow-motion merger. They would have touched with the gentlest of pressures, their surfaces of ice and rock softly compressing against one another, their individual gravities finally fusing them into a single, lumpy whole. This slow, careful union would explain the extreme elongation without the need for a violent, fragmenting impact. The two progenitor bodies would have never fully mixed into a sphere, forever preserving the memory of their dual nature in Varuna's awkward, potato-like silhouette. For this to be possible, the original two objects would have needed to be of similar size, a pair of cosmic twins whose combined gravity was just strong enough to hold them together, but not powerful enough to remold them into perfect roundness. This theory paints a picture of the early Kuiper belt not just as a place of violent collisions, but also of delicate gravitational choreography, where worlds could form through patient, gentle accumulation. So what would prove this hypothesis true? The most definitive evidence would come from a close-up visit from a spacecraft. A detailed map of Varuna's gravity field would reveal its internal structure. A contact binary would likely have a double-lobed mass distribution, with two distinct centers of gravity corresponding to the two original cores, hidden beneath a unified surface. We might also see a telltale groove or a deep saddle-like depression at the point of contact, a permanent seam in its geology. From our distant vantage point, more refined observations of its light curve could also provide clues. A contact binary might exhibit a specific, complex pattern of brightness changes that a single, elongated body would not, a subtle flicker encoding the ghost of its dual identity. Confirming this would do more than just solve the mystery of one world's shape. It would reveal a fundamental pathway for how planetary building blocks came together, showing us that some of the solar system's most enduring structures were forged not in fire but in a slow, frozen embrace. The same radiation that paints Varuna red may also be sculpting its very substance. Galactic cosmic rays are not gentle sunlight. They are atomic bullets, the shattered nuclei of long-dead stars accelerated to nearly the speed of light. For billions of years, this invisible hail has been relentlessly striking Varuna's frozen surface, and each impact is a tiny explosion of energy. This is the mystery of its influence, an unseen force that has been slowly and patiently cooking the chemistry of this distant world. When a high-energy cosmic ray slams into a simple molecule of frozen methane on the surface, it doesn't just warm it, it blasts the molecule apart, breaking its atomic bonds. The resulting fragments are highly reactive, desperate to form new connections. In the extreme cold, these fragments quickly recombine, but not into their original, simple forms. Instead, they assemble into increasingly large and complex organic molecules, the same reddish, tar-like tholins that give Varuna its color. This process transforms the pristine, volatile ices into a resilient, dark crust. The true puzzle is not that this happens, but how deep it goes. The penetrating power of these cosmic rays is immense, but not infinite. They can only alter the top few meters of the surface. So the depth of this irradiated layer becomes a cosmic clock. If Varuna's surface has been perfectly stable and undisturbed for the entire age of the solar system, the layer of tholins should be thick, a deep, dark crust measuring several meters down. But if the tholin layer is surprisingly shallow, it tells a different story entirely. It suggests that Varuna's surface is geologically active, or at least frequently churned. Recent cryovolcanic flows, the gentle settling of its rubble pile interior, or even impacts from smaller objects could be constantly stirring the pot, burying the old, irradiated material and bringing fresh, pristine ice up from the depths to be bombarded anew. The thickness of this dark crust is therefore a direct measurement of its history, a record of how often this frozen world has turned itself inside out. A strange flicker in the data caught a watchful eye. In 2020, an alert from the amateur astronomy community suggested something unusual. Varuna had briefly, unexpectedly dimmed. While this single report was almost certainly an observational glitch, a trick of the atmosphere or equipment, it opens a thrilling line of thought. What if a world like Varuna could change suddenly? The forces at play there are slow, measured in millennia, but they are not inert. Imagine a cliff of water ice, weaker than rock and brittle in the deep cold, finally giving way under its own weight. A massive landslide would expose a vast, bright scar of fresh ice, momentarily increasing the world's reflectivity before the dark red tholins slowly reformed. Or picture a small, unseen chunk of rock, a leftover from the solar system's formation, finally crossing paths with Varuna after billions of years. The impact would throw up a plume of fine, brilliant ice crystals, a temporary cloud of glittering dust that could subtly alter the light we see from Earth. The most tantalizing possibility is a belch from within, a late-stage cryovolcanic burp. A pocket of volatile gas trapped for eons finally finds a weakness in the crust and vents into the vacuum, carrying with it a spray of bright, reflective particles. These events would be fleeting, lasting perhaps only days or weeks before the surface settles back into its ancient equilibrium. This is where the global network of dedicated amateur astronomers becomes vital. Professional telescopes are powerful, but their time is precious and scheduled years in advance. They cannot watch every distant world every single night. It is the countless volunteers with their modest but persistent setups who keep a constant vigil on the sky. They are the ones most likely to catch the unexpected glimmer, the anomalous dip in brightness that signals a distant world is still alive, still capable of surprise. That single, unconfirmed dimming is a powerful reminder that the story of the outer solar system is not fully written, and that anyone looking up from their backyard could be the first to witness a new chapter begin. The faint gravitational tugs that guide Varuna may not come from the Sun alone. Its wild, detached orbit places it among a small group of celestial recluses, objects whose paths are so stretched and tilted that they seem almost untethered from our star. This strange orbital clustering is not random, and astronomers now see it as a cosmic clue pointing toward the grandest unsolved mystery of our solar system, the potential existence of a true giant, a hidden world we call Planet 9. The orbits of Varuna and its scattered kin appear to be herded, their farthest points from the Sun, their aphelia, all grouped together in a way that defies simple chance. It is as if we are seeing the footsteps of a flock of sheep, all marching in the same direction, but the shepherd remains invisible. Varuna, in its lonely journey, becomes an unwitting signpost, its path a single day to point in a vast celestial map used to triangulate the position of this hypothetical behemoth. The theory posits a planet up to 10 times the mass of Earth, tracing a colossal 20,000-year orbit far beyond Pluto. Its immense gravity would act like a slow, deep pendulum, pulling on the orbits of these distant Kuiper belt objects over millions of years, aligning them into the peculiar configuration we observe today. Without this hidden shepherd, their synchronized paths are incredibly difficult to explain. So the hunt for Planet 9 is not a search through a telescope's eyepiece, but a painstaking process of celestial deduction. Scientists run thousands of complex computer simulations, testing different masses and orbits for the hypothetical planet, seeking the one configuration that perfectly reproduces the real-world paths of Varuna and its kin. Each new discovery of a distant object like Varuna adds another constraint, another clue that narrows the possible hiding places in the sky. This transforms our understanding of Varuna's significance. It is no longer just a solitary world with its own strange properties, but a critical piece of evidence in a revolution that could rewrite our solar system's family portrait. The very forces that may have exiled it to the frozen darkness could be the same ones that now point the way to a discovery of epic proportions, a hidden member of our Sun's family that has been waiting in the dark all along. The cosmic hunt for a hidden planet is a modern quest, yet the name Varuna itself is a whisper from ancient times. This designation was not a foregone conclusion, but the result of a subtle debate among astronomers. When this distant world was first discovered, the tradition was to name such significant Kuiper belt objects after creator deities from world mythology. The name Varuna, drawn from the ancient Hindu Vedas, was a perfect and poetic fit. Varuna is a supreme god, a divine sovereign who presides over the cosmic order, the night sky, and most fittingly, the waters. The connection is profound, a world composed largely of water ice spinning in the celestial ocean of space, named for a deity of the very same element. This was not the only name considered, however. Some astronomers argued for other mythological figures, sparking a quiet controversy over which culture's stories would be etched onto our maps of the solar system. The choice of Varuna over other potential names is a mystery of human choice, a reflection of how we seek to connect our newest discoveries to our oldest stories. It ties this frozen, physical object to a rich tapestry of human belief, where a god who once measured the paths of the sun and moon now lends his name to a distant, tumbling world. This layer of cultural meaning transforms Varuna from a mere day to point into a symbol, a bridge between the meticulous observations of modern science and the timeless human drive to find meaning in the heavens. The name is a reminder that every number we calculate and every spectrum we analyze is attached to a story. And in this case, the story is one of cosmic waters, both ancient and eternal. A dedicated spacecraft racing toward Varuna is the ultimate dream for planetary scientists. Imagine a mission designed not for Mars or Jupiter, but for this specific, tumbling world on the solar system's fringe. The journey itself would be an epic feat of engineering and patience. Just reaching Varuna would demand a flight lasting decades, perhaps half a century or more, a silent voyage through the profound emptiness of the outer dark. The spacecraft would need to be a marvel of self-sufficiency, carrying its own nuclear power source because the sun is too distant for solar panels, and engineered to remain functional for the entire lifespan of its designers. The payoff, however, would be a revelation. As the probe finally approached, its cameras would begin to resolve a shape that is currently just a flicker of light. We would no longer be inferring an elongated form. We would be staring directly at a cosmic potato, its strange contours and sprawling landscapes unveiled for the first time. We would see if it is a contact binary with a clear seam marking where two ancient worlds merged, or if its shape is the result of a single, shattering impact. The spacecraft's instruments would map the entire surface, identifying those dark and bright patches from the light curve as specific geological features, perhaps vast impact basins, sprawling plains of dark tholins, or even the gentle domes of ancient cryovolcanos. It would analyze the surface composition in exquisite detail, telling us definitively what ices and organic molecules are present and in what ratios. A simple flyby would answer most of our fundamental questions, but an orbiter would transform our understanding entirely. To slip into orbit around Varuna would require a complex and fuel-intensive braking maneuver, but the reward would be a complete and systematic study. We could measure its gravity field, revealing whether it is a solid world or a porous rubble pile. We could search for any trace of a tenuous, seasonal atmosphere. We could precisely determine its mass and density, finally solving the puzzle of what this world is truly made of. Every mystery we have explored, from its frantic spin to its potential for hidden oceans, would be brought into sharp, undeniable focus. This future mission remains a blueprint, a set of calculations and hopes, yet it represents the next great leap, the moment we reach out from our pale blue dot to finally touch one of the most enigmatic sentinels of our solar system's dark frontier. What profound truth about our own cosmic origins is waiting there, silently spinning for us to discover? Its official status remains a ghost in the celestial machinery, a question mark hanging over this distant world. Is Varuna truly a dwarf planet? The answer is not as simple as you might think. Officially, it is considered a likely dwarf planet, a strong candidate, but it has not yet received the formal designation from the International Astronomical Union. The debate hinges on three clear criteria: First, the object must orbit the Sun, which Varuna unquestionably does. Second, it cannot be a moon, and Varuna travels in its profound solitude. The third requirement, however, is where the mystery takes root. A dwarf planet must have sufficient mass for its own gravity to pull it into a state of near roundness, a condition called hydrostatic equilibrium. And this is the heart of the classification puzzle. Our best evidence strongly suggests Varuna is not round at all, but dramatically elongated, shaped more like a stretched egg than a neat sphere. So how can a world that fails the roundness test still be a prime candidate for dwarf planet status? The resolution lies in the subtle nature of gravity and composition. Scientists theorize that Varuna is a rubble pile, a loose aggregation of ice and rock held together by gravity. For such a fragile structure, its rapid 6-hour spin creates immense centrifugal forces that actively work against gravity's pull, stretching the world out. The question then becomes, is its gravity strong enough to make it round if it were not spinning so frantically? Would this collection of cosmic rubble, if given a moment of peace, slowly settle into the spherical shape that defines a planet? Or is its elongated form the true, stable shape for an object of its specific mass and construction? This is not just semantics, it is a fundamental inquiry into what this world is at its core. The uncertainty forces us to look closer at every other elongated object in the Kuiper belt, wondering if our definitions are too rigid for the messy, chaotic reality of the solar system's frontier. The classification of Varuna hangs in the balance, a single world holding the power to challenge our entire understanding of what makes a planet, dwarf or otherwise. The ultimate mystery of Varuna is not one we can list or even name. It is the profound and humbling unknown, the vast territory of questions we have not yet learned how to ask. Our current science, for all its power, is a flashlight beam in a cavern of infinite darkness. We can measure its spin, model its shape, and theorize about its interior, but these are just shadows on the wall. What truly lies beneath that dark, reddened crust? What utterly unexpected feature would a spacecraft's camera reveal as it closed in for the first time? Perhaps we would find something that shatters all our models entirely, a series of perfectly geometric structures, not built by any hand, but formed by some bizarre and unknown geological process. Or a vast subsurface network of interconnected brine channels, a labyrinth of liquid weaving through the ice, hosting chemistries we cannot yet conceive. Maybe its surface is etched with patterns that tell a story of a different kind of solar system formation, one where the rules of physics played out in ways we have never witnessed. The greatest discovery about Varuna could be something our imagination has failed to provide. Every mission to a new world has delivered a shock, a feature that was not in the textbooks. Jupiter's moon Io was predicted to be a dead, cratered world, but we found it ablaze with volcanoes. Pluto was thought to be a simple ball of ice, but we found towering mountains of water ice and vast, flowing glaciers of solid nitrogen. Varuna, spinning in its silent, lonely orbit, holds the same potential for astonishment. Its final and greatest secret is the one it keeps from us, the surprise that waits not just for better technology, but for a brighter spark of human curiosity. The true mystery is that we do not know what we are missing, and that is the most thrilling reason of all to keep looking. From its frantic 6-hour spin to its strangely stretched-out shape, Varuna defies every expectation. We have journeyed through 25 of its deepest puzzles, from the absence of an atmosphere and its profound cosmic solitude, to the secrets locked within its low density and deep red crust. We have pondered its potential as a primordial time capsule, the thermal discrepancies that hint at a complex interior, and the tantalizing possibility of hidden liquid oceans warmed by radioactive decay. Its wild orbit serves as a clue in the hunt for a hidden planet 9, while its very classification as a dwarf planet remains a subject of debate, challenging our definitions. This world is a symphony of contradictions, a place where gentle formation theories clash with violent collisional histories, and where the faintest whisper of sunlight might still choreograph slow seasonal change. Varuna stands as a brilliant reminder that our own solar system, right here in our cosmic backyard, is still a place of profound and thrilling mystery. Each unanswered question is an invitation to explore further. So tell us, which of these 25 enigmas captured your imagination the most? Was it the possibility of a hidden ocean, its role in the search for a giant unseen planet, or its lonely, tumbling journey through the dark? Share your thoughts in the comments below and subscribe to join us as we continue to unravel the greatest enigmas of space.